Maximum and minimum problems. We're going to look at different ways of solving maximum and minimum problems. This first technique we're going to look at is using quadratics. So the idea of quadratics to solve it. Because the graph of a quadratic, as we know, is a parabola. So depending on whether it's concave up or concave down, it's very easy to find a maximum or a minimum point. It's just the vertex of the parabola. The question is, are we interested in the x value or the y value? And once we know that, we can solve the problem. So let's just, forget about an actual word problem. Let's make it a parabola itself and simply say, well, what's the maximum value of this? Minus 3x squared plus x minus 5. Now, it certainly has a maximum value because we know this one's concave down. Yes, I could find the axis of symmetry and substitute in, but I don't need to because it's not asking me about the x value. It's just saying how high up does it go. So if I just find the y value of the vertex, and I'll do that using the discriminant idea, or I could do that by completing the square. So let's use the completing the square idea first of all. Now when I complete the square, I prefer the coefficient of x squared to be 1. So the first thing I've done there is factorise the negative 3 outside of just the x terms. I'm not really concerned with the constant at this stage. So I want half the coefficient of x squared. So half the coefficient x will be 1/6. Square it, that'll be it's not 1/12. It's going to be 1/36. But remember, we got negative 3 times that. So that's why we're adding 1/12 there. To get us back to negative 5. There it is, completed. So the vertex of our parabola, sure, I know what the x value is, I can work it out, but I'm not really interested. I just want the y value, and I've got minus 4 and 11/12. Personally, I wouldn't use that technique. I'd go the discriminant way. I just think it's quicker. If I work out the discriminant, it's minus 59. And remember, we said the y value is minus the discriminant on 4a. So I can simply go, okay, minus the discriminant on 4a, minus 59 on 12, bang, I've got the answer straight away. I think that's a quicker way of finding the y value. So minus 4 and 11/12. Well, let's make a word problem. Here we go. A rectangle, perimeter 64 centimetres. We want this rectangle to have a maximum area. Okay, so there's my rectangle. I know the perimeter is 64, so let's give it some dimensions. I'll call one side creatively S for side.
Wow.
Yes, I know. Thought of that myself, you know. Now we know the perimeter is going to be 64, therefore the other side must be 32 minus whatever S is. It's the area I'm trying to maximise, and there's my quadratic. S times 32 minus S. So really, all I have to find here is the axis of symmetry. See, it's the dimensions we're interested in here. It's not actually what the maximum area is. It's the dimensions that would get the maximum area. So it's in this case, the S value. But that would be the axis of symmetry of our parabola. So there it is, 32S minus S squared, which I could factorise, complete the square, do it that way, and we get 16 by 16. How else could I have done it? I could have gone minus b on 2a. That's probably going to be quicker, again, than completing the square on it. And that would get me 16. It brings up an interesting fact that when we're trying to maximise shapes, there always turns out to be the perfect shape. So the perfect rectangle is a square. A perfect triangle is the equilateral triangle. Things like that. So if it was a rectangular prism, you'd end up with a cube. But don't just assume that, because sometimes they'll put some variations in that certain dimensions are restricted by things like that. But very often you'll find these are the answers. Okay. So multiples of 3. Now, of course, you'll know they're multiples of 3 when what will happen?
The digits add together.